Hello, I'm Neeraj. Today I will try to explain the bias variance trade-offs. Actually, bias variance trade-offs contains three terms: bias, variance, and trade-offs. So first of all, we will try to understand the bias, then variance, then relations between bias and variance, and we use these relations to understand the trade-off between them. This is very important because it will help you to design the best or optimal model for any machine learning and deep learning architectures. So let us start with the bias. When we train or design any machine learning or deep learning model, we generally focus on two different things, like what is the predicted value, what is the given value. So bias is actually the difference between the predicted value and given value. High bias means the difference between the predicted value and given value will be high, and low bias means the difference between the predicted value and given value will be low, means your model is better. Actually, bias totally depends upon the architecture or machine learning models that you design. So, whether you provide infinite amount of data, once you designed a machine learning or deep learning model biased towards something, so it will not change. Means it is architecture dependent. So, we can understand the bias by using simple mathematical format also, applicable to regression or classification both. Suppose we use the term estimator. So bias is the difference between estimator, expectations of estimators, and the parameter or thing that we want to achieve. So this is very simple. Now the next part is the variance. So variance shows that how much your predicted values are scattered or at what distance from each other. So high variance means the predicted values are at very high distance from each other. Low variance means they are at lower distance from each other. We can also understand variance like how our machine learning or deep learning architectures behaves on different training data set, or how our architecture is over specialized towards any training data set. We can also understand the variance as how our past models accuracies are away from the model of average quality. So this also gives the information about variance. So we can understand the variance in the similar fashion by using the estimator. So variance of any estimator, that theta hat, can be given as expectation of estimator square minus expectations square of expectations of estimator, or we can simplify this like expectations of estimator minus given parameter or the target that we want to achieve, and then take the square of that. So this is the way we can mathematically define the term variance. Now we can also understand the term bias and variance in the context of machine learning. So suppose we are going through some ensemble method like bagging. To understand what is the bagging, bootstrap aggregation, random forest, you can watch my previous other video tutorials that clearly explains the bagging process, bootstrap aggregation process. Here for explanation, I am just considering that our system, suppose our bagging system takes a sample x and y from the dataset through the bagging process. Now, suppose we apply some hypothesis h1 on dataset x and it gives the result, suppose YA. Again we apply some hypothesis H2 on the same data set, and it gives the result YB, and so on. Suppose we have total n models, n hypotheses, and we apply, and then it gives some data like n kind of thing. So these are our predictions, and this is our actual prediction. So in that case, variance will be just variance of h1x, h2x, and till hnx. And what will be the bias? So bias will be like average of predictions by all hypotheses h1, h2 till hn minus our actual prediction value. So this is a way to understand how bias and variance actually, we can define bias and variance in the machine learning, and similarly we can define this for deep learning architectures also. We generally use the bull's eye representation to understand the bias and variance and its actual impact on the results. So we will try to understand like how the low bias, high bias, the combination of low bias and low variance, low bias and high variance, and all those combinations, how they will predict different results. So we will assume that our red circle shows the correct class, shows the correct area of correct result, and these are like how we are scattered. These other lines are like shows that how we are scattered from or away from the actual results. So when we say that low bias and low variance, low bias means our model complexity is optimal enough that it will not show any biasness towards the training data set, and low variance means our model is sufficient, or we provide a sufficient training data set, we apply sufficient strategy to get the low variance. So in that case, our predictions will be very much near to concentrated, very much near to the actual prediction area. Now suppose what happens, we little deviate from low bias to high variance, then what happens? Our low bias and high variance case. So low bias means the gap between predicted value and actual value will be low, but high variance means they will scattered at higher distances. So prediction value will be at higher distances but near centered near to the central area. So you can see here. Now again, high bias and low variance. So high bias means your training data set is too weak. So your model is too weak and biased towards the training data set, towards some things, whether you provide any kind of training data set. But low variance means you are trying to provide very good training data set, but your model is not sufficient, very good. Then in that case you will face the problem of high bias and low variance. So here you can see that due to low variance, or the distance between the points are low, but as the bias is high, so the results are biased towards some points. So you can see the group of some data at a particular point away from the actual center. Now you can see the high bias and high variance. In that case, you may assume that your data is crap, your model is also almost crap. So in that case, you can see that there is no relations between the results, actual results, and the actual predicted results and the requirement. So in that case, the model is too weak. Now We will use this understanding, like how the bias and variance affects the result predictions. One more thing that I want to explain here. In the case of bagging related discussions, we just assumed that the irreducible error or errors are zero. So we are not considering the noise. So this happened in the case of absence of noise. So in the case of noise, we can add some noise parameters also. The derivations will be little different. But without noise, you can use this as a standard means mathematical representations for bias and variance in the case of ensemble techniques. Now we will try to understand the relations between bias and variance, and then we will try to achieve that what is trade-off. So in general, machine learning or deep learning, we take the training data set and test data sets. We use validation data set also with the training data set to optimize our model, but here for simplicity we will just consider that we are using training and test data set. Before going into the details, first let us explain that I have used a simple graphical structure to explain the relations between bias and variance. This is y-axis and this is x-axis. So our y-axis represents the prediction error, x-axis represents the model complexity. So prediction error, here you can see the low prediction error, here you can see high prediction error, here you can see low model complexity, here you can see the high model complexity. Now let us start with our training data set and start building our model. So we started building model. At initial our model complexity is too low, prediction error will be very high, means training error will be very high. So we started creating model, increasing the complexity of the model. Sorry. So we started the complexity of the model, and after certain time you can find that it is when we highly increase the model complexity, the prediction or training error is low and almost reach the minimum points, possible points. Now we start with our test data set. So we took our test data set. So at the starting point, we will achieve low variance plus high bias. Low variance and high bias, because at this point our model is at very initial stage and may be biased towards a certain kind of things. So it will show the results like this: high bias and low variance. So the results at this point will be scattered around this. Now we will start testing different models, like here our model's complexity is high, so little high complexity model. As we go, after certain time we will find that this type of behavior, means when we start testing our test data on the model that we build with little higher complexity, our prediction error was low. At a certain time, like at this point, when we find that our training error is low, but prediction error started increasing. And at this time, at this point, like similar to this, we will achieve like high variance plus low bias. So this type of phenomena that we will achieve. Now you may ask questions that what is the model complexity? Means how we assume that how we understand that what is model complexity. Suppose you are using your deep learning architecture, then increase in model complexity means increase in different tools of deep learning, like you can add some LSTM layers, you can add CNN layers, you can add more DNN layer, You can increase the number of layers in your deep learning architecture. You can increase the density of your deep learning architecture. You can make more condensed or bigger deep learning network. So this is like your model complexity. So as you increase your model complexity, so after certain time you will realize that your training accuracy is very good, but test accuracy is very poor. Means after this time, means after this area, your system is just over learning or over classifying. It started over classifying, like overfitting. Means it started memorizing the training point. And so when we get some test, unknown and unseen test data, it will start showing the wrong prediction results. So your prediction error started increasing. Now we will try to understand that what is the optimal area here where we can get the minimum or optimal prediction error in both our training and test data set. So we find that this is our point. This may be somewhere in between or near to that area. So at this point you will find that your designed model or architecture shows the best performance in the form of training and test both data sets. Means its precision will be high, prediction error will be low, kind of things. So you can assume that this part of your area will be known as underfitting, and this will be overfitting. Why? Because before that, this line, you find that you are started, means your maturity of your model, complexity of your model is increasing. Means till this area, your model before this area or before this line, means that line is known as trade-off line. You can assume it like a trade-off line which shows the best performance. So before the trade-off line, your model complexity is not so high that it can shows the best predictions on your trading data set. It may have some biasness towards the due to architecture. So the system will be underfit, means it will not show the good performance. But after this line, what kind of phenomena that you will achieve? Your system will start memorizing the data, over classifying or the data. In that case, it will not show the very good performance on your data, and it will show the overfitting characteristics. So what is the overfitting characteristics? Actually, suppose it is very easy to understand. Suppose you are training your machine learning or deep learning architecture, that if length and width of a particular two sides of a rectangle is like 2 3, then this same length like 2 2 3 3 4 4, then it is a square, and your data is like till 5. You have taken all the data till that, and after that you have just this range of data with so many decimal points also, 4.1 4.2 4.1 4.1 5.1 5.1, like so many data, but data in this range only. And you train the data by using highly complex model. Then your model, your trained model will memorize that if the sides is between, means side 1 is between 2 to 5 and side 2 is also between 2 to 5, then it is square. And in other case, it may be some other architecture. So if you give the something like 6 and 6, it is again a square kind of architecture, a square shape, but your model will not be able to recognize if it overfits. So this is the problem, and this is the simple definitions of overfitting, like how the system starts memorizing those points, and then it gives the poor performance. Now, this curve also gives some other information, like how you can improve your system. Now, suppose you are at this stage, your system starts overfitting, then how you will achieve at this point? To achieve at this point, the first point will be reduce the model complexity. Means you can reduce some layers in the deep learning architecture. As we discussed, just discussed, like in overfitting also related to the data sample. So we can improve our data, like we can give more variations in our samples. Third, maybe if you are using the computer vision, then it may be like a data augmentation. You can apply flip image, different kinds of image, so that system can understand the new data easily and avoid overfitting situation. You can use some regularization technique. So in deep learning, I have already discussed regularization techniques in some other videos. So some regularization techniques like dropout and general regularization, L1, L2 regularization you can use. L2 regularization mostly you can use. So in the dropout, what will happen? Actually, it is already explained. So I am just briefly giving here. So suppose this is our architecture, simple neural network architecture, like that. So in the case of dropout value, suppose we take the dropout value 0.5, then all the values which are less than 0.5. So some nodes will be out in some calculations. So you can see some different at the different times. You can see some different ensemble kind of architectures that it creates, and it will help in reducing the overfitting scenarios. And in the case of machine learning, the best solution, if you are overfitting and variance is high, the best possible way is to use the bagging technique. So random forest, you can use the random forest, and the random forest here will help you in reducing the variance without much affecting the low bias situation, if you are going through to the machine learning. And these are the scenarios when you are using the deep learning architecture. Now, suppose you are at this point and you want to reach here, then what you will do? Suppose you are already using regularization technique, then you can reduce this value, dropout value you can reduce. You can redesign your L2 regularization values or reduce its value also. Here variation of data will not help, because underfitting is totally highly depends upon your model architecture. So you have to increase layers or improve your model architecture. If you are using the machine learning techniques, the next thing you can do, you can use increase the number of features, so that machine can easily understand the patterns and you want to reduce the bias, then you have to go for boosting techniques. Like XZ-boost, gradient boostings. So all those boosting techniques sequentially reduce the error. For example, gradient and XZ boostings, they use the gradient based techniques to slightly reduce the bias, and through that you can also get here. Means so in summary, if you are using machine learning techniques, you have to add more features. You can apply boosting techniques. If you are using deep learning techniques, reduce the dropout, reduce the L2 regression, increase the number of layers, improve the model complexity so that it can best represents the data. So these are the key things. Till that time, we have used this is our training feature related curve, this is our test feature related curve. So we represents this curve as a bias square, and we can take a variance curve also. So this represents the how variance differs. Like when we reduce the model complexity, our variance is reducing. Suppose we introduce irreducible error also, like the error that we cannot remove by changing the model. So in that case, we say that this is our error, prediction error. So upper side of this curve shows the prediction error. In the case of underfitting, this is in the case of overfitting. So it will be our total error. And by considering the variance, bias, and irreducible error, we can define the formula for total error. In the next tutorial, I will try to achieve this, derive these relations. So till now, I just described that how we get the total error through bias and variance, introducing bias and variance in the means trade-off curve, trade-off graph. So thanks for watching.